Well, we're back here for another round of screws, fasteners, and non-permanent joints. I'm going to dislocate my keyboard and concentrate on the tablet here. I would concentrate on example 8.1. It covers just about everything we've done so far, except a couple notable exceptions. It does not cover Acme threads or single thread, triple threads. Example 8.1 is a double thread, square thread. So it's 8.1 as a double square thread. Whoop. And somehow I've lost my eraser ability. There it is. Double square thread example. So by virtue of being a double square thread example, it does not have single thread, triple thread, or Acme thread. In order to compensate for that, I've got the handwritten example following example 8.1, and that covers a single Acme thread example from start to finish with torque to raise, torque to lower, everything, pretty much everything example 8.1 does, just Adam's own. But whoa, still getting used to this here. Adams' own example. And that's handwritten following example 8.1 in the slide stack. As I was going through these notes, I realized there's one thing in the power screw section that's completely missing, that is extraordinarily common, and that is ball screws. They're totally not covered in this section, but they ought to be. In terms of positioning, these are mostly for position, not load. If you want something that's fast to position something accurately, it's a ball screw. And this is a recirculating ball screw. So right here I'm going to box the word recirculate, and I don't really like how I boxed it, so I'm going to box it again. So the balls recirculate, so essentially this ball goes around to here, which goes around to here, which goes around to here, which goes around to here. So this is a recirculating ball screw. So you basically have a ball bearing action. There we go. Basically have a ball bearing, a very smooth ball bearing action, and recirculates either way, so it's just as good as the screw, if not better in some instances. Here's example 8.1. Again, it's a square thread power screw. They give you the dimensions, and they give you the coefficient of friction and the load on the screw, and they want you to find all this stuff, which they do pretty well. They go through this in detail. I'm going to gloss over this because you should be going through this by yourself. And you notice one thing though, that when they find torque to raise, that it includes something that is not in there. Let me flip back to where their formulas are. Torque to raise. Torque to raise. They're using a different formula than 8-1. Here's 8-1, and there's something off to the right here that's missing. It's the collar friction, and there it is, right there. And that's what I was saying along several slides ago, is that you have to include collar friction for torque to raise, and for, by the way, torque to lower, there's collar friction. So here we have two instances where, let me find the equations in the book that are wrong. 8-1, equations, and 8-2 are wrong. And here we see the perfect example of it in example 8.1, where they include collar friction. Whoops. So collar friction must be included. Double underline. So the example 8.1 basically makes my point for me, that their equations are a little bit misleading. And then we have efficiency. Again, don't care. I really don't care about efficiency. Again, you'd really only be worried about efficiency of a power screw if you have high speeds and multiple reciprocations, that kind of thing, where you're trying to calculate energy expenditure or size of motor. That is I guess a decent amount of applications for that, but there's a total lack of treatment of that in the book. So of how efficiency would calculate into that even. So, I mean, there are important things for this efficiency calculation, but it is completely insufficiently covered. Let's see, we've got stresses. Again, you notice that they're using the 0.38. That's, again, I could find the spot in the book here. I'm flipping through the book here rapidly. Whoops. What happened? There we go. The actual breeze of my page turning affected my tablet. That's odd. Anyhow, you notice that there's a 0.38 in there, which is not in the formula in the book. That's a little disturbing. Check my notes from the previous slides. Definitely want to check the notes from the previous slides. No, I don't want to add a device. Thank you. Anyhow. So they're using 0.38 because the first thread of the arrangement takes up 38% of the load. So it's 38% of load on first thread. All right, and so they make mention of that in the text, but they don't actually put that into equation form until they get to the example here, example 8.1, and all of a sudden there's this thing that's very different. This equation here and this equation here is very different than what's in the book. And you know, your first inclination is, where the hell did that come from? Well, it's explained previously by me in the slides above. The rest of this is pretty straightforward. Just want to point out we're using von Mises stresses. That's also what SolidWorks Simulink, SolidWorks Simulation uses. So von Mises is, let me erase that. Von Mises stress is very common. I mean, basically, if SolidWorks Simulation will plot von Mises stress, I believe by default, and that's generally what's taken as the static failure criterion, just in general. That would tie into distortion energy theory from Chapter 5. If you want to find the maximum shear stress, you could do the stress transformation. They do that here, and they're going to find the maximum principal stress, sigma 1 here, is 48.7 megapascals. Other than that, they find, most importantly, the maximum shear stress, which is sigma 1 minus sigma 3 divided by 2. And this is really where, if it's steel, it's going to rip along that direction. Here's the handwritten example. Obviously, I did this example in my own hand. So it follows A through F, similar to example 8.1, except it has a single Acme thread. At least I think it does. Let me just check. Yep, single Acme thread. So the previous example had a double square thread. Let me just write that here. So the purpose of this example is to give you an idea of where the lead and pitch go into the equation, and also how the Acme thread equations go in. So lead versus pitch, and Acme versus square equations. And I'm not going to dwell on it. Go through it on your own. It does everything else the same as example 8.1, except for a single thread Acme thread. Table 8.4, pretty useful. If you're gonna calculate stresses, there are safe bearing pressures available in the book, and this is the important part here. This is the speed. This is an FPM equals feet per minute. Let me just, I'm looking at that right now. Screw bearing pressure, notes, low speed. Yep, just reading the book on the side here. 10 feet per minute, not very fast. 50 feet per minute, that's about almost a foot per second. So you can see that higher speeds for power screws is so higher speeds for power screws is approximately 1 foot per minute. But that's where we get into recirculating ball screws, which go much faster than that. I'm sorry. That was incorrect. It was approximately 50 to 60 feet per minute. And this is why we have recirculating ball screws. Can go faster than that. And then you don't have to worry about what materials. So we have screw material and nut material. And with recirculating ball screws, we really don't have to worry about that, and we can exceed those speeds. And that's why I wish they were in this section, but they just aren't. Another couple useful tables. So these are useful design tables. They contain the basically friction coefficients. That's the ever-elusive friction coefficient. So here they have some estimates. Pretty good place to start. They use some of these in the problems in the end of the section, but aside from that, this is actually just a pretty good place to start if you actually have a design application. So we're transitioning now from power screws to bolts and bolted connections. Head type bolts, pretty common. The hexagon head bolt, I'm sure you've all seen one of these. Hexagon head bolt. Usually uses a nut, fairly heavy duty. There's different versions of these nuts and screws. Hexagon head cap screw, socket head cap screw. This is actually something I've seen a lot of right here. Socket head cap screw is extremely common. Oop. Still getting used to this, sorry. I love the eraser tool. Very common. In terms of machinery in the field, you have top access, don't need a wrench. For power machinery, you usually want the precision application and access from the top. These are for general assembly. Obviously, they're extraordinarily common, but when you get to the socket head cap screw, that's usually for more complicated pieces of machinery where you need a little bit more precision. Machine screws, this is the kind of stuff you can find at Home Depot a lot. And believe me, I go through there all the time. I've been there recently looking at trying to find something specific, and Home Depot is not the greatest resource. There's also McMaster-Carr. Rewrite that. McMaster-Carr, and a couple other ones, but machine screws, smaller sizes. If you go someplace like Home Depot, you'll find a lot of oddballs, and but they actually do conform to the standards that are in these following slides. So here's the one that I found at Home Depot that I was really surprised. Wasn't the binding head or I think it was the truss head. I think they had an actual package labeled as a truss head, And I was like, what the hell is that? And then I came home and found this lecture, and I'm like, oh, that's what they mean by that. But anyhow, I didn't buy that screw, and it was Phillips in the Home Depot package. But you know, all these things have a purpose, but most of it doesn't really matter, except for if you want a recessed head, and you know how you want it accessible from a tool. The actual grip and length of what's actually happening with a thread is kind of independent of what's happening with the head of the bolt. But if we focus in on the hexagon head bolt, obviously they're one of the most common. We got some standard dimensions in table A29, and if you're just looking to throw them into a design, the width between lands is usually about 1.5 times the nominal diameter, and the bolt length is measured from below the head. So this is the length. That's not equal to the threaded length. That's something you need to be aware of. If you're specifying bolts, there's actually a methodology to how much of the length is actually threaded. So if you specify a 6-inch bolt, it will not necessarily be threaded the entire 6 inches unless you specify it that way. So the L sub T is defined as the threaded length, and there's actually a formula for that. Threaded lengths, speaking of which, there's an English and a metric version, but let's say you just go to Home Depot and look through various hex head bolts. You will find that this is actually pretty accurate. I'm going to erase that. It's actually pretty accurate. At Home Depot. And what you'll find is Home Depot almost definitely doesn't have the hex head bolt that you need, and therefore you will have to find another supplier. As far as nuts go, we're looking at Appendix A31 for typical specifications. Keep in mind that the first 3 threads of a nut carry the majority of the load. That also means that the first 3 nuts of the screw and the bolt slash, can do that better. So the first 3 threads of both the nut and the bolt carry the majority of the load, particularly the first thread. This main thing is, if you're going to load up your bolt to close to the proof load, you should probably not reuse it, because the first thread is likely to have plastically deformed. Okay, this next section is a major section, so I'm gonna call this the end of part 2, and head into part 3 after this. I just want to give you some foreshadowing that as we get into this section, what we're really after here is flange separation. Is when do we actually lose clamping? So, you know, when you have this separating force P, when does the actual force between these surfaces equals 0. If you have a sealing surface there, that becomes a major problem. So I'm going to end it here, and we'll continue it with tension-loaded bolted joint, and then get around to loss of clamping in a tension-loaded bolted joint. I'm going to have to, sorry, I should have ended it right there, but I'm going to have to actually reattach the keyboard and hit Control R. There we go.